All the sugar in your blood is 1 teaspoon. That is all of it. Across every artery, every vein, every capillary you have, roughly 4 grams of glucose dissolved in about 5 liters of blood. And in a few minutes, you are going to eat something that contains 10 times that much. Most people think insulin exists to deal with that sugar. That is the part everyone was taught. It is also the smallest part of the job. So what is insulin actually doing in there? Why does a hormone named after sugar spend most of its effort on fat? And what exactly breaks years before anyone calls it diabetes? It starts in an organ that weighs less than 100 grams, your pancreas. Buried inside it are roughly 1 million microscopic clusters of cells. They are called the islets of Langerhans. The islets of Langerhans are tiny islands of hormone-making cells, scattered through the pancreas like seeds through a loaf of bread. Inside those islands sit the beta cells. Beta cells are the only cells in your entire body that can make insulin. Not the liver, not the brain. No backup organ anywhere. There are between 1 and 3 billion of them, and put together they weigh about 1 gram. 1 gram of tissue stands between you and a disease that used to kill children in a single year. So how does 1 gram of tissue know when you have eaten? It does not taste anything. It counts. Glucose drifts into the beta cell on its own, through doors that are always open. Inside, an enzyme called glucokinase grabs it and tags it. Glucokinase is slow, and that is the entire point. It works at exactly the concentrations your blood actually reaches, and it never runs out of capacity. So the faster glucose arrives, the faster it gets tagged. That tagging feeds a furnace, and the furnace makes ATP. ATP is the cell's energy currency, and its level rises in step with the sugar outside. Sitting in the membrane is a channel that leaks potassium out of the cell. Rising ATP snaps that channel shut. The moment it shuts, the electrical charge across the membrane collapses. Gates swing open. Calcium floods in, and calcium is the trigger. Packages of insulin that were already sitting near the wall move up and dump their contents into the blood. That is the entire sensor. An enzyme that counts, a channel that closes, and calcium. It is worth knowing because an entire class of diabetes drugs does exactly one thing. It closes that same potassium channel by hand, and it does not release insulin in a steady stream. The islets fire in pulses, a few minutes apart, all day long. The liver is tuned to that rhythm. Give it the same total amount of insulin as a flat, constant drip, and it responds less than it does to the pulses. The pattern is part of the message. There is a detail in how insulin is built that turns out to be useful. The beta cell does not make insulin directly. It makes a longer single chain called proinsulin, then cuts a piece out of the middle. What is left, still held together at the cut, is insulin. The discarded middle is called C-peptide. For every molecule of insulin released, exactly 1 molecule of C-peptide goes out with it. But C-peptide is not destroyed by the liver, so it lasts far longer in the blood. That makes it the honest witness. If someone is injecting insulin, a blood test cannot tell whose is whose. C-peptide can. It is how you find out whether a pancreas is still working at all. Insulin itself is small. 51 amino acids, folded into 2 chains and pinned together by bridges of sulfur. It was the first protein human beings ever fully sequenced in 1955. And once it leaves the beta cell, it survives about 5 minutes. Here is what those 5 minutes buy. You eat. Within 2 minutes of glucose arriving, the beta cells release insulin they had already made and stored. Somewhere between 30 and 60 minutes, the level in your blood peaks. By 2 hours, if everything is working, it is falling back toward baseline. And by 3 hours, it is close to where it started. That entire curve runs 3 or 4 times a day, every day, whether you notice it or not. But that curve is not one smooth release. It arrives in 2 waves, and they are made of different things. The first wave is insulin that was already packaged and waiting against the wall of the cell. It fires within about 10 minutes, and then it is spent. The second wave is insulin. The cell builds on demand, and it keeps coming for as long as the glucose stays up. The first wave is the small one. It is also the one that matters most, because its job was never to clear the sugar. Its job is to tell the liver to stop adding more. Remember that wave. It comes back at the end of this video, and it is the first thing to go. There's also something strange about how the whole system gets started. Swallow a glass of glucose, then on another day, put the identical amount straight into a vein. Same sugar, same rise in the blood. The mouthful triggers far more insulin than the injection does. Most of the difference comes from your gut. Cells lining your intestine detect food arriving and send hormones ahead of it, warning the pancreas before a single gram of glucose reaches it. Your pancreas is not only reacting to your blood, it is being told what is coming. That advance warning accounts for a large share of the insulin released after a normal meal. It is also the mechanism behind the best-known weight loss drugs of the last few years, which are copies of one of those gut signals. But the first place insulin goes is not your muscles. The vein leaving your pancreas does not run out to your body. It runs straight into your liver. Your liver meets insulin before anything else does, at concentrations 2 to 3 times higher than the rest of you will ever see, and it destroys roughly half of it on the first pass. Half the insulin your pancreas makes never reaches the rest of your body at all. That first pass has a consequence almost nobody mentions. When your own pancreas makes insulin, your liver gets a strong dose, and the rest of you gets a weak one. That gradient is the natural state, and every tissue in you is built around it. Insulin from a syringe does not take that route. It goes into the tissue under the skin and joins the general circulation. It reaches the arms and the legs at full strength, and the liver at a fraction of what it was designed to see. So injected insulin is not a copy of yours. It is the same molecule delivered to the wrong address. The message it delivers there is not take in sugar. It is stop making it. Because between meals, your liver is a sugar factory. It breaks down stored glycogen. It builds brand new glucose out of amino acids. It runs all night, which is the only reason you do not collapse in your sleep. Insulin is the signal that shuts the factory down, and insulin never works alone. In those same islands, sitting right beside the beta cells, are the alpha cells. Alpha cells make glucagon, and glucagon tells the liver the exact opposite thing. Start making sugar. Break down the stores. Put glucose into the blood. 2 hormones with opposite instructions, made a few thousandths of a millimeter apart, draining into the same vein toward the same liver. And your liver does not obey either one on its own. It reads the ratio between them. When you eat, insulin climbs and glucagon drops, and the balance swings hard toward storing. Between meals, it swings back the other way. This is why insulin on its own is a bad way to think about any of this. The liver is not following an order. It is reading a balance, and either side of that balance can fail. Only then does the rest of the message go out. In your muscle and your fat cells, insulin locks onto a receptor sitting on the outside of the cell. That sets off a chain of signals on the inside. And at the end of the chain, something physical happens. Tiny packages holding a transporter called GLUT4 travel to the cell surface and fuse with it. GLUT4 is a door for glucose, and without insulin, it stays parked inside the cell where it is useless. So insulin does not push sugar into your cells. It opens the doors and lets the sugar walk in. Your skeletal muscle takes up close to 80% of everything cleared this way, which raises an obvious question. If glucose needs a door opened for it, what about the organs that cannot afford to wait? They were never on the system. Your brain takes glucose without asking anyone's permission. So do your red blood cells and the lining of your gut. Their doors are open all the time. That is not an oversight in the design. It is the design. Your brain is about 2% of your body weight and burns around 20% of your glucose, and it cannot store any of it. A brain that had to wait for a hormone would go dark every time the hormone was late. So insulin does not run your body's whole sugar supply. It runs the optional part. Now here is the part that reframes the entire hormone. Of all the jobs insulin has, the one it is most sensitive to is not glucose at all. It takes remarkably little insulin to do it, far less than the amount needed to open a single GLUT4 door. And what it does at that low concentration is tell your fat cells to stop releasing fat. Every fat cell you own is constantly leaking fatty acids back into your blood. That is not a malfunction. That is your fuel supply between meals. Insulin shuts it off. So when insulin is high, fat stays in. When insulin is low, fat comes out. Insulin is not the sugar hormone. It is the switch between two entirely different ways of running a body. Fed and storing, or fasted and burning. And it flips that switch at a lower dose than it needs for anything else it does. We know exactly what happens when it disappears, because for most of human history, that was a death sentence. Before 1922, a child diagnosed with type 1 diabetes lived about a year. Without insulin, the fat switch is jammed open. Fatty acids pour out. The liver makes ketones. The blood turns acidic. Those children were not killed by high blood sugar. They were killed by a body that could not stop burning itself. On the 11th of January 1922, in Toronto, a 14-year-old named Leonard Thompson became the first person on Earth to be rescued by an injection of it. That first injection almost did not work. The extract was crude. It left an abscess in his arm, and his blood sugar barely moved. A biochemist named James Colleb spent the next 12 days purifying it. The second attempt, on the 23rd of January, worked. His blood sugar fell, and the ketones cleared. He lived another 13 years. It is worth being precise about what failed in that boy, because it is not what fails in most people. In type 1, the beta cells are destroyed. The immune system attacks the islands, and the factory is gone. There is no amount of trying harder that brings it back. In type 2, the factory is still standing. The insulin is still being made, often in larger amounts than normal. What has changed is everything downstream of it. The same hormone, the same molecule, and two failures that have almost nothing in common. There is one more thing that does not fit the sugar story. Protein raises insulin too. A steak with almost no carbohydrate in it still triggers a release. Because insulin was never a glucose alarm, it is a storage instruction, and amino acids need storing as well. And there is one more job that has nothing to do with either. Insulin crosses into the brain. There are receptors for it in the hypothalamus, the region that keeps track of how much fuel you are carrying. When insulin arrives there, the message is not about the meal in front of you. It is a report on the size of the reserve. More fat stored, more insulin in circulation, and more of that signal arriving upstairs. It is one of the ways a body holds its own weight roughly steady across years without anyone deciding to. So insulin is not only a storage instruction, It is also the message that says how much has already been stored. Which brings us to what actually breaks. It is not the beta cells, at least not first. It is the listening. The receptor is still there. The insulin is still there. The signal inside the cell simply gets quieter. So where does the quiet come from? The best supported answer is fat sitting in the wrong place. Not fat under your skin, and not the number on a scale. Fat inside the muscle fiber itself, and inside the liver cell. A muscle fiber was never built to store much of it. When more fatty acids arrive than it can burn, the leftovers pile up as half-finished molecules with a name worth hearing once: diacylglycerol. Diacylglycerol switches on an enzyme inside the cell, and that enzyme goes and puts a chemical mark on the very first link of the insulin chain. Marked that way, the link still works. It just works worse. The receptor caught the hormone, and the message got muffled one step later. This is why two people who weigh exactly the same can have completely different results. It is not how much fat you are carrying. It is whether it is sitting where it belongs. So the beta cells do the only thing they're able to do. They make more. And this is why nobody notices. For years, sometimes more than a decade, that compensation works perfectly. More insulin, same blood sugar, a completely normal test result. Blood sugar only climbs when the beta cells finally cannot keep up. And there is an early sign for anyone who bothers to look for it. Remember the first wave, the packaged insulin that fires inside the first 10 minutes. That wave is the first casualty. In people who go on to develop type 2 diabetes, it is already blunted while the ordinary tests still come back clean. The liver never gets its early instruction to stop, so it keeps pouring sugar into a meal that already had plenty. Researchers followed 6,538 British civil servants all the way to diagnosis, and then looked backwards. Insulin sensitivity had already been falling for 5 years before anyone was diagnosed with anything. By the time a glucose test looks wrong, the thing it is measuring has usually been wrong for a very long time. So when someone calls insulin the sugar hormone, they have the story backwards. Sugar is what insulin gets measured by. Fat is what it actually controls. And the pancreas is the organ that pays for both. Which leaves one obvious question. If insulin has been running high for a decade before a single test shows it, what has it been doing to the organ that sees it first? That organ is your liver. And that is a very different story.